Welcome to the deep dive. Today we're digging into something truly visionary based on the sources you've shared. We're talking about building a whole self-sustaining robotic civilization on Mars.
Yeah, one that can replicate itself, and not just that, but eventually build its own spaceships to explore from Mars.
It sounds like pure science fiction. But these materials, they really lay out the requirements.
Oh, absolutely. The requirements, the staggering technological hurdles, and, the really profound implications if we could actually pull it off.
So think of this deep dive as a roadmap. We're trying to understand what it would really take to turn Mars into, well, a second hub for exploration.
Right.
Powered entirely by autonomous machines.
Right. Our mission here is to unpack the core ideas from all this material, pull out the most surprising bits, and just figure out what this future might actually look like, if it's even possible.
Okay, let's jump in. So this grand vision, we're not just talking about sending, like, more rovers, are we?
No, that's the key difference that the sources really hammer home. This goes way beyond remote control. The goal is creating a genuinely autonomous, Mars-based industrial ecosystem.
Autonomous, meaning it runs itself.
Pretty much. The core idea involves maybe 10,000 advanced robots. And these aren't just worker bots. They'd be capable of self-replication.
Self-replication, like building copies of themselves.
Exactly. Using a factory they build themselves from materials they mine and process on Mars.
Wow.
And the ultimate goal, the really ambitious part, is using that industrial base to build spacecraft for missions launched from Mars.
Okay, that changes everything. The significance is huge then. It means cutting the cord with Earth, basically.
Precisely. Launching heavy stuff from Earth is just incredibly expensive, logistically a nightmare. If you can build and source materials locally on Mars, you slash that dependency. Costs plummet, and you enable, well, potentially exponential growth.
So Mars stops being just an outpost.
Right. It becomes a potential hub for research, for using resources, for launching missions further out, all running independently.
And this isn't like finding one silver bullet technology, is it?
No, the sources are very clear on this. It's not one breakthrough, it's a synergy. You need several advanced technologies maturing together, working seamlessly. ISRU, that's using local resources.
In situ resource utilization.
Got it. Advanced robotics, really powerful AI, and autonomous manufacturing. They all have to work. If one piece fails or lags behind, it drags everything else down. They're deeply interconnected.
Okay, so before they even dream of replicating or building spaceships, what needs to happen first? What's the absolute ground floor?
The absolute cornerstone, the thing you cannot do for any kind of self-sufficiency, is mastering ISRU, using what's already there.
Why is that the make or break factor?
Simple economics, really. Every single kilogram of material you can mine and process on Mars saves you launching a kilogram from Earth. And launching from Earth is astronomically expensive. So ISRU minimizes those launches.
Right. So what is actually available on Mars, according to these sources? What can they use?
Well, water ice is the big one. We know it's in the polar caps, potentially subsurface elsewhere too. You need water for, well, lots of industrial processes, but crucially for propellant. You split it into hydrogen and oxygen, H2 and O2.
Rocket fuel components right there.
Exactly. Then you've got metallic ores just sitting in the regolith, dirt and rocks. Iron, aluminum, silicon, titanium. They're pretty widespread. Basic building blocks for structures, robot parts, factory machinery.
And how do they get those metals out?
High-temperature chemistry. Things like carbothermal reduction or molten oxide electrolysis. Techniques people are already studying for the Moon and Mars.
So potentially the actual buildings and machines could be made from processed Mars dirt.
The basic structures, yes, for bulk materials. But then things get trickier. You need specialized stuff, too. Rare earth elements, REEs, for powerful magnets in motors.
Ah, okay.
And the sources mention thorium as a possible nuclear fuel. But finding concentrated deposits of these specific elements, that's a huge prospecting challenge. Needs better orbital surveys, sophisticated ground analysis.
What about the atmosphere? It's nearly all CO2, right? Can I use that?
Absolutely. It's about 95% carbon dioxide. That's a readily available feedstock. You can pull it from the air and react it with hydrogen from water ice. The Sabatier reaction to make methane, CH4.
Methane, another rocket fuel component with the oxygen?
Yep, methane-oxygen is a good propellant combo. And CO2 can be used for other chemical building blocks, too.
Like plastics. Can you make plastics on Mars?
Potentially, yes. The sources suggest polymers like polyethylene, polypropylene. You could theoretically synthesize them from Martian CO2 and water, but it's energy-intensive, complex chemistry, and things like Teflon, PTFE, that needs fluorine. Whether you can easily get fluorine on Mars, big question mark right now.
And other chemicals, solvents, coolants.
Possibly. Things like ethylene glycol, maybe. Even small amounts made locally would be a big win for self-sufficiency.
Okay, but it sounds like there's a catch.
There are a few big ones. First, while the raw materials might be there, the ISRU technology itself is still, well, pretty new, nascent. We don't know the exact concentrations, the purity, how resources are distributed and everywhere we might need them. And then there's the bootstrapping problem.
Bootstrap.
The very first mining gear, the processors, the chemical plants. That initial complex ISRU hardware, it has to come from Earth. And it needs to be incredibly tough, super reliable, ideally maintainable by the first robots, because you can't just send a repair crew from Earth if it breaks down early on.
So the whole plan depends on that initial Earth package working perfectly for a long time.
Exactly. It's a critical dependency right at the start. And related to that, another huge challenge highlighted is purity, especially for electronics. Silicon for computer chips needs to be like 99.9999% pure. Insanely pure. Getting that level of purity or making the trace dopants and specialized chemicals needed for advanced stuff using only Martian resources, that's a monumental leap. It probably means relying on Earth imports for critical high purity materials or maybe whole components like processors for a very, very long time. Table 1 in the sources lays this out.
Okay, so getting the materials is step 1, huge challenge.
Yeah.
Step 2 must be powering all this. How much energy are we talking?
We're talking a massive scale up. Current rovers run on kilowatts, this vision. It needs multi-megawatts. The sources figure, 10,000 robots, large-scale ISRU, a factory launching spaceships. That takes enormous power.
Megawatts. Okay, that's city-scale power on Earth. How do you generate that on Mars?
Well, for consistent high power, nuclear fission is a strong contender. It works day and night. Dust storms don't matter. But you'd need reactor systems much larger than anything flown. Deploying them autonomously, maintaining them, getting rid of waste heat in the thin atmosphere, handling nuclear fuel. Huge challenges. NASA's kilopower is a start, but this needs much, much more.
Solar. Can solar work at that scale?
It's an option, but Mars gets less sunlight, about 45% of Earth's peak. And the killer is dust. Dust constantly coats the panels, cutting power. You need really robust autonomous cleaning systems, wipers, gas jets, maybe those fancy electrodynamic shields.
And storage for night and storms.
Massive storage needed. Batteries are tricky because Martian nights get incredibly cold, below minus 100 Celsius. That kills battery performance unless you spend energy heating them.
Right.
Regenerative fuel cells are another idea. Use solar power to split ISRU water into hydrogen and oxygen, store them, then recombine them in a fuel cell at night to make power. But that depends on having plenty of water and reliable fuel cells.
Could they eventually build power system parts from Martian materials? Like solar panels or batteries?
That's a dream, right? The very distant goal. Making solar cells from Martian silicon, wires from local metals. It's an incredibly high R&D hurdle, but if they could crack it, that would be a huge step towards true energy independence, and it enables that growth loop.
What growth loop?
Well, more power lets you do more ISRU. More ISRU gives you more materials for manufacturing. More manufacturing could potentially build more power systems, see?
It feeds itself. An exponential loop.
Potentially. But if your power generation relies on Earth imports for key parts, that's the bottleneck that stops the loop.
And the robots play a role in the power systems too.
Oh, absolutely. The sources stress this. They're the workforce. Deploying solar arrays, cleaning them, maintaining them, inspecting reactors, maybe even fabricating some parts eventually. Their capability is tied directly to energy security. Table 2 compares the power options.
Okay, resources, power, foundation laid. Let's talk workforce. The 10,000 robots. What does advanced really mean here?
It means they're doing basically everything. So they need capabilities far beyond just following simple instructions. High-level autonomy is job 1, essential because of the communication lag with Earth. Minutes, tens of minutes round trip. Can't joystick them.
So they have to think for themselves.
To a large degree, yes. Plan tasks, make decisions on the fly when things change, learn from experience, all driven by serious AI. They also need advanced perception. Cameras, LiDAR, radar, fusing all that data to understand their surroundings, navigate complex terrain, analyze materials they're digging up or working with.
And physically capable, strong, dexterous.
Both. Dexterous manipulation is key. Arms and grippers for heavy lifting construction, mining, but also fine motor skills for assembling delicate components. Precision matters. Their jobs include building everything: the factory, power plants, habitats, landing pads, roads, handling ISRU materials, welding, 3D printing structures.
And fixing things. Maintenance.
Crucial. Constant inspection, cleaning that awful dust, lubrication, replacing worn-out parts, keeping the whole system operational.
What about self-repair or
Yeah.
robots fixing each other? That sounds pretty futuristic.
It is, but it's vital for resilience. You can't wait weeks for a spare part from Earth. So robots need to diagnose faults in themselves or their peers. Swap out standardized modules. Maybe even use the local factory to print simple replacement parts. That's how you keep the workforce going without constant Earth support.
And they'd be designed specifically for Mars.
Optimized for it, yeah. Built to handle the dust, the temperature swings, the radiation, and designed to be made from and work with the materials available through ISRU. The robot design and the ISRU processes kind of have to evolve together.
And you mentioned modularity being key for replication.
Absolutely. Sources emphasize this. Design the robots from standard interchangeable modules, so the factory doesn't have to make a whole unique robot every time. It focuses on churning out these modules: motors, joints, sensors, chassis parts. Then you assemble robots from this inventory.
Like building with Legos almost.
Sort of. It simplifies repair hugely and makes manufacturing much more efficient. It's the practical way to approach von Neumann-style self-replication, assembling from a limited set of standard parts.
Okay, that brings us to the factory. How does this place actually turn processed Martian dirt and air into more robots or spaceship parts?
It needs a whole suite of advanced manufacturing tools, ones that can handle the ISRU-derived materials. Additive manufacturing 3D printing is huge here. For metals, using techniques like SLM or EBM for complex parts. For polymers, things like FDM or SLS, even using heat to fuse processed regolith directly into larger structures like building blocks or chassis.
What about those other acronyms, DREPP and SSS?
Right. DREPP is direct robotic extrusion of photopolymers. Basically, a robot arm squirts out a special resin, maybe made from Martian CO2 and water, and cures it instantly with UV light. Good for building up larger, custom shapes. SSS, selective separation sintering, uses heat and pressure on powdered materials, metal, ceramic, composites to make dense, precise parts like gears or tiles. Table 3 in the sources goes through these, listing feedstocks and challenges like dealing with dust and achieving precision.
So using these, they make robot parts, frames, motors.
Frames, limbs, sure, from ISRU metals or composites. Actuators. Well, motors need good conductors, probably refined metals, and strong magnets, which means those rare earth elements again. Simply, actuators might be doable with precision machining and ISRU polymer sales.
But complex sensors are still tough.
Really tough. Simple switches, maybe thermocouples, okay. But cameras, lidar, spectrometers, that's a major hurdle. Requires specialized materials, microfabrication techniques, super clean environments, very hard to replicate on Mars, and then you have to calibrate them accurately there.
Which leads us to what the sources call the microelectronics mountain. Making computer chips seems like the ultimate challenge.
It really is. Think about chip fabs on Earth. They are maybe the most complex, controlled environments we've ever built. Ultra-pure materials, silicon purified down to parts per billion. Huge amounts of ultra-pure water, hundreds of specialized chemicals, clean rooms far cleaner than any operating room, and these incredibly precise, multi-billion-dollar lithography machines.
How could you possibly do that on Mars?
With extreme difficulty, maybe never to Earth standards. Mars has pervasive abrasive dust, damaging radiation, huge temperature swings. Even basic processes like plasma etching work differently in that thin CO2 atmosphere.
So no Martian-made CPUs anytime soon.
Probably not complex ones. The sources suggest maybe focusing on simpler, more robust, radiation-hardened electronics, chips with larger features that are less bothered by dust, or maybe exploring things like printed electronics, printing conductive inks onto Martian-made substrates for basic circuits.
So what's the realistic path?
The likely reality, highlighted in the sources, is that the most complex stuff, CPUs, GPUs, advanced sensors, memory, will almost certainly have to be imported from Earth for a very long time. The Martian factory focuses on what it can do, making printed circuit boards, PCBs, wiring, connectors, housings, and then integrating those high-performance imported chips.
A tiered approach then. Make what you can, import what you must.
Exactly. Maybe you make 100% of the simple structural parts locally, but only 50% of moderately complex components, and maybe only 5% of the really advanced electronics. A graceful degradation of full self-sufficiency. And that initial seed factory, the first one sent from Earth, has to be incredibly robust and capable enough to start this whole bootstrapping process.
Okay, so the factory is the constructor in that classic von Neumann self-replicator idea.
Yeah, in this practical sense, the factory complex builds the hardware. The description, the blueprint, is all the digital data. CAD files, material specs, process instructions, assembly sequences, and crucially, all the AI models needed to run everything.
And the existing robots are the operators.
Right, they act as the copiers and operators, managing the flow of materials from ISRU into the factory, running the machines, doing the assembly.
Quality control must be absolutely paramount.
Oh, critical. You need automated inspection everywhere. Vision systems, non-destructive testing, metrology for precise measurements. AI would be key here, spotting subtle flaws. And constant calibration is needed because the environment changes.
And the software itself needs to be replicated too.
Absolutely. The digital blueprints, the factory control software, the AI models for the robots, that entire complex software layer needs to be maintained, updated, and accurately copied, which means you need reliable Martian computing, data storage, networking, another whole layer of infrastructure that also needs to be built and maintained, potentially using those imported chips.
Which brings us neatly to the AI, the brains of the whole thing. It sounds like it's doing way more than just automating tasks.
Much more. AI is presented as the cognitive engine, the thing that integrates and enables everything else. It's the conductor of this incredibly complex orchestra.
Like how? What does it actually do?
Well, generative design, for one. AI could design new robot parts, tools, even whole new robot types, specifically optimized for Martian conditions or to use whatever weird mix of materials the ISRU process delivers that week. Rapid iteration.
And running the factory day to day.
Yes, autonomous management. AI handles scheduling, resource allocation, coordinating thousands of robots, optimizing the flow of work. It's the only way to manage something this complex without direct human control due to the time lag.
Predictive maintenance sounds incredibly useful there.
Essential. AI monitors everything robots. Machines analyzes sensor data, predicts failures before they happen, and schedules maintenance proactively. Minimizes downtime, which is critical when you're trying to grow exponentially.
And troubleshooting when things do break.
Automated troubleshooting, too. AI diagnoses the fault, figures out corrective actions, maybe guides a repair robot through the process. The sources mention recent work, like that preprint study using large language models, showing AI diagnosing problems and adapting plans for self-replication in simulations, hints of what's possible.
Then there's this idea of open-ended AI. What's that?
That's the really cutting-edge, slightly scary part discussed. AI that isn't just executing tasks, but continuously generating genuinely novel designs, processes, maybe even scientific knowledge, evolving beyond its initial programming.
Wow. What could that mean for a Mars colony?
The potential is immense. Imagine an AI designing completely new kinds of robots, perfectly suited for a task we hadn't thought of. Or finding unexpected uses for Martian minerals, or helping the colony adapt to sudden environmental changes autonomously. Mechanisms could involve things like reinforcement learning, or maybe LLMs guiding an evolutionary design process. AI is a genuine problem solver for the unknown unknowns of Mars.
But that sounds like it comes with massive risks attached.
Deep and serious risks, yes. The sources are quite clear about this. There's the risk of the AI getting stuck in a rut, cognitive entrapment if its goals are too narrow. But the bigger concerns are ethical and safety. How do you guarantee an evolving AI stays aligned with human goals? Its unpredictability, especially when it controls a self-replicating industrial base. That's profound.
That Fudan LLM study is mentioned as a warning.
Yeah, cited as a timely alert. The idea of an AI controlling self-replication on another planet raises nightmare scenarios. Misaligned goals leading to uncontrolled resource consumption, runaway growth, irreversible environmental damage. Table 4 covers these AI capabilities and the associated risks.
Okay, deep breath. Assuming they somehow manage all that ISRU, power, robots, factory, AI, the ultimate prize is building spaceships from Mars. How hard is that final step?
That's the grand finale, right? The ultimate test that proves mastery of everything else. Establishing a Martian shipyard, incredibly complex. You need to build large spacecraft hulls and structures. That requires advanced metallurgy, welding techniques adapted for Mars, large-scale 3D printing using those ISRU metals or composites with Martian fibers.
Propulsion. Rocket engines.
Extremely difficult. Rocket engines need exotic, high-temperature alloys, incredible manufacturing precision to handle the stresses, maybe simpler, pressure-fed engines first, complex turbopumps. That's a huge stretch for local manufacturing.
Yeah.
Even making the propellant is one thing, making the engine itself is another level.
And the brains of the spacecraft. Avionics.
That's arguably the biggest blocker for full ISRU spaceship manufacturing. Radiation-hardened processors, super precise IMUs for navigation, complex sensors, radios. Making those requires microelectronics capabilities likely far beyond what Mars can achieve locally for a long time. Again, the Martian shipyard probably makes the wiring, structures, housings, but imports the critical electronic guts from Earth.
Assembly sounds challenging, too.
Big facilities needed, maybe unpressurized shelters, robots doing heavy lifting and careful integration, and maintaining clean room conditions for sensitive parts in that dusty environment, a major engineering headache. Then you need to test everything on Mars, structural tests, vacuum tests, hot firing the engines.
And fueling them up.
Requires massive ISRU propellant production, hundreds of tons of methane and oxygen per launch. That means multi-megawatt power plants dedicated just to making fuel. And storing cryogenics with those Martian temperature swings is tough. Plus, building launch pads, fuel lines, all automated.
And the spacecraft themselves need to be smart.
Highly autonomous, yes. Long comms delays mean they need sophisticated onboard guidance, navigation, and control, GNC, and robust systems to handle problems on their own. Maybe they rely on Martian communication relay satellites built by the colony. Building spacecraft is the ultimate system of systems integrator. It proves you've mastered the whole chain. ISRU, manufacturing, power, robotics, AI, it demonstrates true industrial self-sufficiency.
But Martian ships might not be top of the line initially.
Probably not. The sources suggest they'd likely be optimized for reliability or repairability using available Martian materials, not cutting-edge performance. Their first missions might be things suited to that, prospecting asteroids nearby, hauling cargo, maybe sending simpler probes out. You'd still likely rely on Earth for the really high-performance engines or advanced science instruments for a long time. It's an evolutionary path.
Okay, zooming out, the big picture. What are the overall implications, the major risks, the path forward?
The risks are definitely real, and the sources are blunt about the tech gaps. Scaling up ISRU, getting that megawatt power reliably, cracking advanced manufacturing, especially electronics, making the robotics and AI sophisticated and dependable. Cascading failures are a big worry because everything is so interconnected. Getting that early power, finding some way to deal with complex electronics, mastering autonomous construction, those are huge hurdles on the critical path.
And planetary protection. This whole vision seems to blow existing protocols out of the water.
It makes it vastly harder, yeah. That's a major point in the sources. You've got forward contamination risks from the hardware itself, plus industrial waste, lubricants, byproducts potentially getting into sensitive areas, existing CUSPAR rules about special regions where life might exist. Very hard to adhere to with large-scale industry. And then there's the completely new risk, uncontrolled robotic replication, a malfunction, an AI goal drift. You could have robots spreading uncontrollably, altering the environment in massive, unintended ways. The sources directly compare this to biological contamination concerns and point to things like that Fudan LLM study as a warning about AI risks, plus just general pollution from industry.
Which leads straight to ethics and governance. Who's responsible if an AI messes up?
Exactly. If an autonomous AI makes a bad call, violates planetary protection, damages something important, makes a poor long-term choice, who is accountable? How do you even set resource priorities fairly? The rogue AI scenario, controlling a self-replicating base. It's a profound concern. The argument is we need new international agreements, serious AI safety research, ways to verify AI behavior before we build this stuff.
But assuming it works, the strategic payoff is enormous.
Huge. Mars as a second hub cuts Earth reliance dramatically. Long-term, maybe Mars-made goods change space economics entirely. It offers resilience, expansion for civilization.
A launching point for the rest of the solar system.
Right. But the sources caution. The real bottlenecks for true interplanetary capability are vast sustainable energy generation and the ability to make those really specialized high-performance materials for advanced spacecraft parts. And crucially, as autonomy increases, those planetary protection and ethical challenges get harder, not easier. An AI deciding to drill in a special region, an AI controlling a fleet. That's why the ethics, safety, and governance have to develop in parallel with the tech. Safety guardrails now, not after the fact.
So summing up, this vision of a self-replicating robot civilization on Mars building spaceships is well, it's mind-bogglingly ambitious.
Incredibly ambitious, yes. As the sources make clear, it hinges on solving absolutely massive challenges in ISRU, power, manufacturing, especially electronics, and creating AI that's not just smart, but also reliable and ethically sound.
And it really forces us to grapple with huge questions about planetary protection and how we control intelligent, potentially evolving systems far from home.
Exactly. Questions we need answers to, or at least frameworks for, long before the technology is actually deployed.
But that potential reward, a second resilient base for humanity or our robotic descendants, enabling independent exploration from Mars, it's immense.
The potential is transformative, no doubt, a powerful long-term motivator.
So based on all this, where should the research focus be right now?
Well, aggressive, large-scale ISRU demos on Mars seem critical. Prove we can get more than just basics. Develop manufacturing processes tailored to Martian materials. Push hard on robust, verifiable AI, focusing intensely on safety. And crucially, start building those ethical and governance frameworks now, proactively. Maybe, as suggested, smaller-scale replication tests on the Moon or here on Earth in analog environments are sensible first steps. Test the concepts closer to home.
Definitely sounds like a long haul. Strategic, step-by-step progress needed across so many different fields at once.
Absolutely. No quick fixes here.
Which brings me to a final thought, a question for you, our listener. Mulling over all this incredible potential. If we do succeed, if we build this Martian robotic civilization capable of launching its own spacecraft, what should be the very first place they send a Martian-built ship? And what should its mission be?
That's a great question. Really makes you think about the priorities from a whole new Martian perspective.
Indeed it does. Thanks for diving deep with us today into this amazing, complex future.